Like Jess Barnes, geologist Katie Joy is fascinated by the far side mystery.
Because people hadn't seen the far side of the moon, we just made the assumption that the far side was the same as the near side. So Luna 3 turned our ideas on its head, and those ideas are still being turned on their head.
Katie is one of NASA's lead investigators, studying the precious Apollo samples to better understand the moon's mysterious past.
Because the moon's surface is very old, it can tell us a lot about history of the solar system's past. It can tell us about Mars, Mercury, Venus, and the Earth. Every time there's new technology, we can ask these rocks new questions, and that's why they're sort of the gift that keeps on giving, because they're always going to be available for us to look at with new ideas.
The Apollo samples continue to teach us about the moon, the Earth, and the rest of the solar system. But when it comes to solving the far side mystery, there's a problem.
With the lunar missions that have been to the surface and collected samples, we've only visited a very geologically restricted area on the near side of the moon. So in order to fully understand the moon and the far side composition, we really need to go back and collect samples from a more diverse region.
And with NASA's Artemis mission, aiming to return humans to the lunar surface in the coming years, Jess is preparing for a new batch of evidence.
We want to preserve that DNA, fingerprints, rocks as precisely as possible so that we don't lose any of that evidence. So before we go back to the moon, we really need to understand what's the best way to curate and keep samples safe and preserve them for future generations.
To get ready for these upcoming missions, NASA is releasing some crucial, untouched evidence from its vaults.
After Apollo 17, people soon realized that it would be beneficial to future generations to lock some of the Apollo samples away in special storage for 50 years. And now we're at the point in time when NASA has decided things have improved so much that we're now at a position to open those samples, use new technologies on them to answer past and new questions.
Now, armed with techniques impossible 50 years ago, Jess is one of the handful of people chosen by NASA to analyze these precious samples.
One of the things that we've been doing is using a particle accelerator to measure the oxidation state of sulfur in our samples. We're really looking at these samples forensically, and this is a really new technique that's been applied to lunar samples only in the last few years. So yeah, bring it up a little bit and we can do a slow scan.
This tool allows Jess to piece together the sample's history and establish how new evidence might be better preserved in the future.
We find that samples that were prepared 50 years ago contain a lot more sulfur than we see in samples that were actually stored frozen for 50 years. We're not quite sure why that is, but this is one of the things that we want to find out. Do we need to do something differently for samples coming back from the moon in the future?
It's a problem that must be addressed before we return for more evidence. Something Jess knows is critical if we're ever to finally solve the mystery of the moon's far side.
This is one of the few places in our solar system where we have a good chance to look for life. There's evidence for a vast subsurface ocean below the icy crust of the moon. The amount of water that's suspected there is many times more than all the oceans together we have on Earth. On the poles, you're approaching minus 200 degrees Celsius. Icicles that could be several meters high might be present. And if you're very lucky, then you might just spot a plume erupting nearby, like an ice volcano that ejects material from the subsurface to enormous altitudes. On top of that, there's a good chance that there's an energy source at the bottom of the ocean, hydrothermal activity, that can support the emergence of life. That makes Europa outstanding. Europa Clipper is the first mission that goes to the outer solar system that has the exclusive goal to investigate the habitability of the body in the outer solar system. It will launch in October 24 and will arrive at Jupiter in April 2030, so it's 5.5 years for Europa Clipper. Jupiter has like about 70 moons, so the number increases like every year by a bit. But there are 4 moons that stand out, that are the so-called Galilean moons. The innermost is Io, then Europa, then Ganymede, and then Callisto. With the telescopic observations before the arrival of the first spacecraft, you could see that some of these moons are really, really bright. They reflect way more light than a rocky surface would. And so, for example, Europa and also Enceladus, they are one of the brightest objects. And so it was suspected already at that time that the surface might be composed of shiny, reflecting water ice. I mean, after the investigations of the Galileo spacecraft in the late 90s, Europa became a prime target in planetary science all over the solar system. Because with a huge subsurface ocean, with the spectrotidal activity, that became the first place that could be habitable in our solar system besides maybe Mars. That immediately sparked proposals of missions to go back to Jupiter and specifically investigate Europa. I mean, if you are a planetary scientist, probably the most rewarding science goal is to see if a planetary body is habitable or actually inhabited. So Europa Clipper will stay in orbit around Jupiter, and in most of its revolutions, it will have a close flyby at Europa. And the flybys are arranged in a way that it's like a web in the end surrounding the moon, that you have in the end a good overview over almost the entire surface after these 50 flybys. During this close flybys, you get an idea of what is evaporating from the surface of Europa. And from that, of course, you learn about the makeup, the composition of the surface. And this is, of course, specifically true if there's plume and venting activity. That's what I really would put a smile on my face, if we could measure plume material that's connected to the subsurface ocean of Europa. The instrument called SUDA, the Surface Dust Analyzer, is the instrument I'm working on. It measures the composition of tiny grains that are surrounding Europa, mostly ice grains. And these grains are knocked off the surface by micrometeoroid impacts. With the SUDA instrument, we can sample these materials, and with that we get an idea about the surface composition. We could constrain what salts were there in the ocean, if there's an alkaline, neutral, or basic environment, if there's hydrothermal activity at the bottom of the ocean, what the organic chemistry inside the ocean has evolved to. Unfortunately, we currently only have one example of a planetary body or a moon where life exists. And so it's very difficult to speculate about the nature of life elsewhere. If we look for signs of life on an icy moon like Europa, it's probably the most straightforward to just look for simple forms of life. If there would be complex civilizations in these subsurface oceans, we probably would have known by now, right? But I know that at least for the life on Earth, the access to oxygen is important to develop complex life compared to simple monocellular life. So this is one of the big science questions that Europa Clipper wants to answer. Has Europa Ocean access to oxygen that is created on the surface? So is material from the surface cycling back down to the ocean? If yes, then oxygen might be available in the ocean, and this opens up the possibility for more complex life. And not just a single cell, but maybe fish-like complex life. Everything between one cell or no life or fish-like life, like complex organisms, that might be even intelligent or not, nobody knows. It's really up in the air. I look very much forward to the launch. It will be launched on a Falcon Heavy that was decided only a few months ago. So one of Elon Musk's rockets. And I'm really much looking forward because I never saw a rocket launch in my life. I like to see it. But on the other hand, it'll make me nervous. So that's always a problem. If rockets have a chance, even the safest rockets have a chance of like a 1% or 2% that there's some failure, and then everything was in vain because all the development has been done. Most instruments have been crafted twice, that you have a spare. So I really hope that the launch will go well. So I think it's one of the most exciting missions there is, and I'm really glad that I can participate in these endeavors.
The prospect of mining the moon is just around the corner. So what are they so excited about? Should we be doing it at all? How would it even work? Let's explore the unexplored. The moon is just a cold, empty rock with nothing of interest but a 50-year-old American flag stuck in the ground, right?
When we arrived there, almost a little bit more than 50 years ago, it's interesting to hear the recordings from the second man on the moon. When he stepped out of the lunar lander and looked around, he said, "This is magnificent desolation." But our view of the moon has changed radically since then, from magnificent desolation to a place that is full of important resources that we may use once we land there. Just to give you an idea of some of those, 45% of the moon is oxygen. It's just that it's tied to the rocks. These are oxidized rocks, but that can be heated and you can extract plenty of oxygen. It's got 21% of silicon for anything that we do with semiconductors, iron and titanium, very important elements, aluminum and calcium and magnesium and things like this, potassium and phosphorus. And also you find radioactive materials like uranium and thorium. Then there is the possibility of finding water. Water exists there, and that can be a total game changer because water not only is good for humans, but mostly for propellant. Because water, you can split it into hydrogen and oxygen, and it can serve as the most energetic propellant that we know.
This is incredibly exciting and really does demonstrate how there are more than enough resources to maintain a permanent base. We've got metals to develop technology and oxygen for breathing. We could use moon rock to 3D print habitats and extract hydrogen to fuel deeper space exploration, which could be a big game changer. But there are actually a couple of really exciting resources that in the future could make sense to bring back to Earth. The first is energy from light. Scientists are trying to look at how we can create solar factories on the moon. Now, the problem comes with how we transport that energy back to Earth. And one way is using microwaves. We could beam them through the atmosphere, through the clouds, and collect them in a receiver here on Earth, which could give us enough power to supply the entire world 24/7. This is still a long way off and doesn't make financial sense yet. But there is an element on the moon that we don't have much of here on Earth, one that could radically shake up the energy industry.
One of those elements is called helium-3. Helium-3 has been identified as a potential fuel for what's called fusion energy. Right now, the way that we obtain nuclear energy on Earth is by fission. You hit an atom, you split it, and in the process, you generate energy. Fusion is totally different. Here, you bring two elements, two particles, and you fuse them. And in the process of doing that, which requires a lot of energy, then a lot of energy is also released, and is released directly into electricity. You don't have to go through heating, and then steam and then producing electricity. And even better, the residue is helium. Just helium, the one that, again, you can use for inflating balloons. So it's a non-radioactive waste that you can get out of that.
So it seems like mining the moon could not only serve us in space, but also provide helpful resources for us back here on Earth. But that's likely somewhere in the future. What about today? There is one resource that countries are especially interested in, and that's rare earth elements. The interest in rare earth elements has exploded because they are one of the main components of the communications industry. Neodymium is used in speakers, lanthanum in lighting, yttrium for computer screens, and gadolinium in X-rays. Despite being called rare earth, they're not actually that rare. The issue is that they're found in concentrated areas, which makes them a highly valuable bargaining chip for countries that have them within their borders. One of the countries that dominates the rare earth industry is China. Because of this, countries like the US are starting to ask questions like, well, what if China decides to restrict access to the US? Where can we get them from? The answer is, you guessed it, the moon! But would the US just be able to go up and take what they want? What are the laws for governing resources in space? The 1967 Outer Space Treaty states that no single country can claim ownership over any celestial body. But it said little about mining. And because of this ambiguity, two schools of thought have developed as to how we interpret the treaty. And this has got space lawyers, space lawyers, debating the issue.
So far, the international discussion has centered around two major viewpoints. The one argues, since the moon belongs to everyone, it means that the resources in the moon's subsurface, whether it's water or iron or gold or platinum, belongs to everyone as well. And you can't allow a single state to say, okay, I'm going there, or I allow my private sector to go there and mine it for their own commercial profit. That's the one interpretation. The other interpretation says, well, it's a global commons, and just like the high seas, once you are there and you do something there, part of the freedom of the high seas / outer space, you can own it and sell it and make money with it. The comparison is then with the fish in the high seas. So these are the two opposing views. We still have no legal agreement amongst all the states that this is the appropriate interpretation. So we still have a ways to go before all the states are on the same page.
Because of this ambiguity, countries are now taking legal matters into their own hands. In 2015, the United States took the first step by saying that any company that sets up operations in the United States will have the right to access, extract, utilize, and even sell resources from the moon. Not own it, but the right to access and utilize it. The following year, Luxembourg became the first European country to establish a legal framework around space resources. After that, the United Arab Emirates joined in, and most recently in 2020, so did Japan. So you're seeing how these countries are moving independently while trying to abide by the United Nations Treaty, but while finding ways to extract resources. But even if we can mine the moon, should we?
That is a concern. Are we going to mine the moon so much that we're going to start changing the face that we see there? Are we extract so many resources that it may affect its orbit or its physical parameters? Some of those concerns are understandable, but some of them shouldn't be of much concern. But in terms of causing major damage on the moon, I think that's not going to happen, at least in many decades or many centuries. But we should start planning ahead on how to do it so that it doesn't cause a problem in the long run.
So should we mine the moon? Well, if you have any interest in travelling to the moon or beyond, or potentially solving our energy crisis, then the answer may be yes, with the caveat that it's done legally and with no irreparable damage. Over the next few decades, the picture is going to start to get clearer as the moon gets busier and we find out exactly what is there and how much of it there is. When that happens, that's when things are going to get interesting. And hopefully we'll be able to find a way to share resources and avoid conflict here on Earth.
Today, I am proud to announce that our next New Frontiers mission, Dragonfly.
So Dragonfly.
Go Dragonfly.
We're building a drone the size of a car and we're going to fly it on a moon.
Dragonfly will explore Saturn's largest moon, Titan.
In 2027, Dragonfly will launch on its 872 million kilometer journey to Titan, the most Earth-like moon we've discovered so far. By the time Dragonfly's baseline mission is over, we'll have flown more than 100 miles, which is almost double the total distance covered by all of the Mars rovers combined. I'm a co-investigator on the Dragonfly mission, and I'm really looking forward to being able to see Titan through Dragonfly's eyes. Titan's been running a big experiment, and it's time for us to go collect the results. Titan is so amazing because in a lot of ways it's very Earth-like. It's the only moon in the solar system that has an atmosphere. It has rain, it has clouds, it has lakes and rivers and sand dunes and mountains. And so, big picture, Titan has all of the things that we think are required for life. We think that there was a period in Earth's history around the time when life originated, when Earth's atmospheric composition was actually probably quite similar to Titan's atmospheric composition today. And so, another one of the questions we have is, what was the chemistry like on the early Earth? How was it related to what's happening on Titan today? And what does that tell us about the origin of life on Earth? Titan is enshrouded in this kind of orangey yellow haze that keeps you from being able to see the surface. And so it was like, okay, we can't see the surface. It's the only moon in the solar system that has an atmosphere. And now we're finding out that there's all of these carbon-containing molecules in the atmosphere that are really, really interesting. And Titan is so interesting that we needed to know more about it. Titan is one of the best, if not the best place in the solar system to fly. If you personally were on Titan and you had some kind of wings attached to your arms for some reason, if you flapped your arms, you would actually be able to fly under your own power. It's that easy. And it's a combination of two things. One thing is that the gravity is pretty low on Titan. It's about 1/7 of the gravity on Earth. So that helps because you don't need as much, energy to get off of the ground. But the other reason why it's so easy to fly on Titan is that the atmosphere is actually more dense than it is at the surface of Earth. So it would be much, much easier, it is much, much easier, I think, to try to figure out a concept to fly on Titan versus trying to send a rover. Dragonfly is not a little backyard drone. It's about the size of a small car. And so that makes it, pretty robust to a lot of things that a backyard drone would not be robust to. Although if it crashes into a tree, as long as we know that it crashed into a tree on Titan, we will be super excited. We will call that a successful mission because we found life on Titan accidentally. We just don't know that much about the surface. And so on the one hand, that's scientifically exciting. And on the other hand, that's a little scary when you're an engineer that's trying to build a spacecraft where you can't, call AAA if something goes wrong. Because of the time delay in light travel between Titan and Earth, Dragonfly is going to have to navigate all on its own. There isn't going to be somebody, sitting on Earth with a joystick flying Dragonfly. There's no GPS at Titan. There's nothing to tell it where it is. Our maps that we have right now are not very good, and so kind of one of these a little bit like, build the plane as you're flying it type things in terms of how we navigate. And basically the way that it's going to be doing that is by taking a really, really lot of images. Where basically every time we fly, we're actually going to fly further than where we want to land so that we can do reconnaissance aerial imaging of the place we think we want to go next. And then we'll turn around and go back to where we had planned to land and land there. Once we tell it, okay, you're going to go do this thing, it will have the whole sequence of what it needs to do. It will be able to make decisions if something goes wrong, and it will decide, okay, this is what I'm doing now. And then, we'll report back and say, look, Mom, I did it. Hopefully. But there's definitely a lot of challenges involved in having these big time delays because we can't control anything in real time. We have all these ideas about the requirements for life. And big picture, we tend to think of the requirements of life as a source of energy, building blocks of life, so like just things that are made out of carbon, and some type of liquid. We think that Titan is a place that it has the possibility of having life. Things that we know we have on Titan are a whole variety of what we call organic molecules. So one of the reasons why we're so excited about carbon when we're thinking about, the search for life and the origin of life is that, selfishly, life on Earth is based on a lot of carbon-containing molecules, and so that's one of the reasons why we're so excited about it. But actually, atomically, it's very interesting. Carbon can make 4 different bonds Whereas when you look at something like oxygen, which can really only make 1 bond or 2 bonds. If you think about your kids' Legos, you can only build so many things with a little like 1-piece Legos, but when you start using the 2 or the 3 or the 4 or whatever, you start to be able to build these really complicated things. And it's the same thing with carbon, because it can make these 4 bonds. It really allows it to make all of these different kinds of molecules, and we think that we see evidence of a lot of that going on in Titan's atmosphere. So we already have a bunch of different simple little Lego structures in the atmosphere, and we just want to know how complicated they got. And whether or not that is kind of similar to the level of complexity that we see on Earth, which might indicate the possibility for the presence of life. And so we want to go and see, with a actual Titan scale laboratory, what has formed from these processes. And so, the more opportunities we have to be able to explore places, the fewer limitations we have on answering our science questions, which is really important.
This guy really needs to stop dancing. Not just because he's terrible, but because the world is running out of helium. But what does that mean for the Large Hadron Collider, MRI machines, and the new space race to mine the moon? Because it turns out helium is way more interesting than balloons. It's actually essential to our modern way of life. And the fact it's running out, well, that is a very big problem. So why is it running out? Well, let's start at the beginning. The very beginning. Right back to the Big Bang. Well, a few minutes after it. That's when the first protons and neutrons collided to form hydrogen, which then fused into the very first helium nuclei. This fusion of hydrogen to helium is in the core of every single star in the universe. And this fundamental reaction paved the way for the creation of all other elements. But even today, 13.7 billion years after the Big Bang, helium still makes up about 25% of the entire universe. So again, how are we running out of it here on Earth? Well, for all its abundance in the universe, it's actually very rare on our planet. Not only that, but it's the only element light and unreactive enough that it can escape Earth's gravity and leak out into outer space. The other issue is that we're using it up.
At the current rate that we're using helium, there have been estimates of about a 100 to 200 years supply. It's the very definition of a non-renewable resource.
So what are we actually using it for? Well, for one, this. The touchdown tradition of the University of Nebraska's American football team, where they released thousands of balloons after the first touchdown. Go Cornhuskers? Okay, we'll come back to this seemingly random example in a minute, because it's actually surprisingly relevant to the story of helium. But helium itself plays a fundamental role in the world today. It's essential in everything from space exploration and quantum computing to medical equipment and the Large Hadron Collider. Its extremely low boiling point means it's perfect for cooling down supermagnets. Meanwhile, its non-reactiveness makes it perfect for producing the semiconductor chips that go into just about every computerized device on the planet. Whatever you're watching this on almost certainly used helium to make it.
Imagine a world without helium. We wouldn't have MRI instruments for medical diagnostics. But also imagine all the things where computer chips are used. Imagine that whole industry was unable to function if we didn't have this special substance.
And that makes the fact that it's running out a pretty huge deal. So much so that the University of Nebraska tradition I mentioned, touchdown pass! Yeah, well in May 2022, this 60-year tradition went on hiatus, and all because of the helium shortage. So thanks Nebraska for taking one for the team. But how on earth have we got to a point where we're relying on college football teams to pitch in and help a global shortage? Well, that story begins with the US thinking helium would win them the war. Yeah, back in World War I, the Germans had hydrogen zeppelins. The US military was jealous. So when a different light gas, helium, was discovered on American soil, they started to store huge amounts of it in a cave in Amarillo, Texas. The National Helium Reserve was born. But fast forward to the 1990s, and the US government decides, time to privatize this bad boy. So it dumps helium onto the open market, cheap helium for everybody. Problem was, that left no incentive for companies to produce their own helium, or recycle any they already had. Enter Helium Shortage 1.0. circa 2006. And since then, we've been hit by shortage after shortage.
Today, there are 4 major suppliers of helium: the US, Qatar, Algeria, and Russia.
To make matters worse, many of the world's helium plants were struck by disasters or political unrest in 2022. Welcome to Helium Shortage 4.0. And just to throw another curveball in the mix, the US government put the rest of its helium up for sale in 2022. So what happens now?
This is a very difficult thing for us to imagine. We would be ceding control of our helium resource to a private entity. We don't even know if helium will continue to be stored there.
So if not there, where? Most of the helium left on Earth that hasn't already escaped into space has been trapped in the Earth's crust.
In many cases, helium is extracted as a byproduct of natural gas. But in Arizona, helium exists in these geologic layers alone.
So for some, the answer is to mine for helium.
What happened in 2018 is it got listed as a critical mineral, and that sort of elevated its status for extraction. So new permits are being issued for helium actively now.
But it's already proving contentious.
In Arizona, the land surface rights are owned separately from the mineral rights underground. So a landowner can have the mineral rights sold from underneath their feet to a company that wants to come drill and extract. We are now at the beginning of modern helium extraction, and so there are no studies on what the environmental impacts are.
So who gets to decide about the extraction process?
The same kinds of stories that the nation, the federal level told itself and others about uranium, it is now telling about helium. And so if national security is the most important thing, and we're in wartime and we need to protect our citizens, then mining X element, whatever it is, to support that national security and defense is the highest priority. If you're living on the land and you care about your future generations and your children and your water and your security, then not mining and not risking extraction impacts at all is the most important priority. I, as an environmentalist myself, have been convinced that there are safe ways to extract helium.
So we need more helium, but we also need to stop our reliance on fossil fuels. Not to mention a checkered history, to put it mildly, of marching into protected environments and mining them to death. And it's not going to get any simpler, because now we've found an even more exciting use for helium.
Helium-3 has been identified as a potential fuel for what's called fusion energy.
Okay, time to get technical, because up until now we've been talking about a specific type of helium, helium-4. Now I want to introduce you to helium-3, an isotope with just one fewer neutron in its core. But that one single neutron makes a huge difference between a supercooling liquid and a potentially game-changing source of energy.
Right now, the way that we obtain nuclear energy on Earth is by fission. You hit an atom, you split it, and in the process, you generate energy. Fusion is totally different. Here, you bring two elements, two particles, and you fuse them. And in the process of doing that, which requires a lot of energy, then a lot of energy is also released, and is released directly into electricity. You don't have to go through heating, and then steam and then producing electricity. It directly goes into electricity. And even better, the residue is helium. Just helium, the one that, again, you can use for inflating balloons. So it's a non-radioactive waste.
Cool. So where do we get helium-3 from? We have a little bit on Earth, including some from dismantling nuclear weapons. But it turns out there's another source of it. Here.
Helium-3 comes from the sun, and that accumulates on the moon at larger quantities that we find here on Earth, because our magnetic field protects us from there.
Overall on the moon, there's estimated to be about 1 million tons of helium-3. And that tantalizing treasure is sparking a whole new space race to get back to the moon. Leading the race are the US and China. China is already searching for helium-3 in lunar rocks brought back in 2020. And they have plans to launch a robotic lunar mission in 2025. Meanwhile, NASA's Artemis program will see humans set foot on the moon again in 2025 to explore the satellite's south pole. So whether it's mining the moon for helium-3 or trying to preserve the helium-4 here on Earth, you're probably about to hear a lot more about helium in the coming years. But does that mean we're just done now for helium balloons? Well, not necessarily.
Those party balloons touch more people's lives and make more people care about helium than they would about other noble gases. You know, nobody's really excited about argon for the most part. And so really helium is special. And again, if we look at it as this special, almost magical substance, then maybe we can see that it's really a gift of the universe to us to have this thing that that allows us to lift balloons and also power rocket ships. What else on Earth can do that for us? So I am not a balloon denier. This is how I put it. I think that people see the magic in helium and it should be shared.